Here's another integration problem for you, and in this problem we're going to determine the mass of a slice, one kilometer thick slice of the mid-ocean ridge complex extending from the ridge crest. Should be over here. This would be a profile of the seafloor away from the ridge crest out to a point where the water depth reaches 4 kilometers. So there's a nice relationship that's been developed. There's a high correlation between the water depth, or the depth to the seafloor, and the distance from the spreading ridge to the 1/2 power. So we've got a couple constants in there. The d0 is just the depth to the ridge axis. It's a constant. We have another constant in here, which just to make things simple, I've let that equal to 1 kilometer. Its units are kilometers to the 1/2, so we have kilometers to the 1/2 times kilometers to the 1/2. Which, sum the exponents, we get kilometers. And so a question that you might think about as we think about putting integrals in action here, we're going to have a definite integral that we have to evaluate. What is this distance x out to a point where the water depth is 4 kilometers? Solve for x. So I've just rearranged things for you here so that you can solve directly for x, and take a second and do that. And you'll find that this distance x is going to be 12.25 kilometers. Okay, so the next thing that we need to do is to develop an integral representation of this ridge area. This is what we'd like, because once we get the area, we can get a volume. You know, it would be the area times 1 kilometer. We give us cubic kilometers, and then if we know the density, then we can figure out what the mass is. But think about this first. What are we getting when we integrate this expression? Well, notice I've plotted the depth axis vertically downward. If I had plotted it vertically upward, that curve would roll up and over. And if we did the integration, we would get the area under that curve. Right? And of course, that is this area. So the area that we're getting when we go through this integration that we have here, this integration, is the area of the water column, not the area of the ridge complex. So we aren't getting this. This is what we want. This is what we have. How can we get this area? Well, realize that we know the dimensions of this rectangular area here. It's 4 kilometers by 12.25 kilometers. We can figure out what this area is. So we can subtract the area of the water column from the area containing both the water column and the ridge system out to a distance of 12.25 kilometers in order to get the area covered by the ridge complex. So this area is 4 times 12.25. That just gives us 49 kilometers squared. So the next thing to do would be to evaluate this integral and show steps. So you might pause the video and go through go through this integration, this definite integral. And so doing that, we find that the integral of d with respect to x is going to be the definite integral from 0 to 12.25 kilometers out of x, d0 plus ax to the 1/2 power. And that gives us two integrals, just taking the constants out. So we get the integral of dx, and we get the integral of x to the 1/2 dx. And so that the integral dx is just x. the integral of x to the 1/2 is going to be x to the 3/2, and then we divide by the new exponent, we get 2/3 times a x to the 3/2, and then we evaluate both of these terms from 0 to 12.25 kilometers. And in doing that, and just kind of working out the steps here, we find that the area of the water column is 34.71 square kilometers. We subtract that from 49 to get 14.29 square kilometers, which would be the area of the oceanic crust out 12.25 kilometers from the ridge axis, down to a depth of 4 kilometers. So the next thing to do would be to assume a density and now calculate the mass of this 1 kilometer thick slice of oceanic crust out to a distance of 12.25 kilometers on either side of the ridge. So we know that what we have here will also extend off in this direction to the left. So we're going to actually have twice this, right? So given that the 1/2 of the area of the ridge extending out to 12.25 kilometers is 14.29 kilometers squared, this area here, the total ridge area extending down to a depth of 4 kilometers from the ridge axis on both sides of the ridge is going to be twice this, or 28.58 square kilometers. In terms of a volume, it's going to be 28.58 cubic kilometers for this 1 kilometer thick slice. So now transform this volume, which is in cubic kilometers, into cubic meters, and then compute the mass using this density in kilograms per cubic meter. Okay, so using this density again, we're going to compute twice this volume, and the density that we're using is, can't remember if I mentioned that, but is 2.9 grams per cubic centimeter, which turns into 2,900 kilograms per cubic meter. And we have, we have 10 to the 3rd meters in 1 kilometer, so we have 10 to the 9th cubic meters per cubic kilometer. So we multiply this all out, and we end up with units of kilograms. We're units consistent. We have 2.86 times 10 to the 10th times 2,900 kilograms, or 8.29 times 10 to the 13th kilograms for the mass, density times volume, of the ridge complex extending 12.25 kilometers to either side of the ridge axis. So we've had to play around with that a little bit to get the volume, but it's a good illustration of integrals, how you can use integrals to help you determine volumes. And the next time we're going to look at area change associated with the formation of a fault propagation fold. So, see you next time. Thanks for joining us.